Good morning, folks. This is the first lecture of week 10. For the past 3 weeks, we have been creating various mechanisms and in CATIA and have been animating some of them, and in fact, we introduced physics in many of those mechanisms, and then plot velocity, acceleration, and stuff like that. But the physics that we introduced really was so simple. In other words, the expression, for example, for the position or the angle was given as a single formula, one-liner, in terms of the angular velocity or velocity of the part, translational velocity. So what we want to do today is to bring some more intelligence into this. In other words, what if actually the physics is more complicated? For example, it involved some if statement. If time is less than this, here's the velocity. If time is bigger than that, here's the velocity. So that we're going to do today, and it is here's the agenda. So I'm going to solve several problems for you. One of them is the very first problem that we did in this course, in this part of the course, namely a block traveling along a path. This is just translating, okay? And the second one is going to be an arm which is rotating about the base, and then I'm going to take both those two and put it on top of each other, so there is a block traveling, and on top of it there's an arm that's turning. We'll get to that later on. Okay, so the very first problem that I'm going to do is right here. It involves just two parts, a block and a track, and the velocity of this block, or actually the position of the block along as a function of time, is given by this expression. In other words, the first 3 minutes, the first 3 seconds, the block is sitting there, and then it starts to it takes a constant velocity and in 4 seconds it takes it to 5 inches down the path, and then it reverses course and then returns with a velocity that is slightly higher back to where it was. Okay, so that's the problem that we're going to do now. Let's go ahead actually and make this assembly. Now the problem is this is so simple that I've already made it. So let me go ahead and get that get the parts for it. So now here is a product. I'm not going to bother making a block. So insert existing components in there, and the two components that I want is just this base and this block. Okay, good, right there. So this is 10 inches long, and the block is 1 by 1. These dimensions have nothing to do with the mechanism or the things that we're going to be doing. Now, let's go ahead and actually create the constraints here. So I'm going to go to the assembly design. Let's anchor the track right there. Okay, and then we create a prismatic joint. So coincidence between this side of the block and this side of the base, and then coincidence between that edge of the block, the track or the base, and let me hide this thing, and this edge of the block. Okay, so this will lead into a prismatic joint, and we have done this thing many times over the past few weeks. And let's move on now. One thing I'm going to tell you, and that is the approach that I'm going to show you is not the only approach. There are other ways of doing this thing, but I find what I'm going to show you the relatively straightforward. Okay, so we're going to go to digital markup, DMU kinematics, get the magic wand out. There's the magic wand. You click on it. A new mechanism number 1, auto create, to create the joint automatically with the magic wand. And of course, there's only a single joint, and it's going to be it's going to be prismatic joint. You can see that. Now, of course, we can make a cartoon out of this. Basically, we go and make this thing a length-driven joint. And I can show you what happens with here. Let's do that. Mechanism can be simulated. If you want to see it, you go and click on animation with command. You can see that it goes 100 inches this way, 100 inches that way. And let me reset it. And the one thing is that if I double click on the prismatic, you notice that there's a little blue arrow here that should be pointing in the direction that I want. If I want to go to the right, I just flip the arrow. But this is exactly what I want. Good. Now, here is the situation. So we cannot write this thing with a single line of code to put the physics into the problem. This is where we have to go, right? F of x, click on the mechanism, select the length, and then say add the formula equal to dot, 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 stuff that we have done. But we can't do that here because there is two conditions to be met. So what we have to do is the following. Let's go back here, cancel that. You have to switch workbenches, although, as I told you, there are ways to do this thing here, but I'm going to take you to a place that you find useful. You have to go there to down all the list of workbenches that we have. You have knowledgeware right there. Remember, here is the digital markup. This is the human builder, or that human builder. This is the analysis and simulation. We don't want these things. We want knowledgeware, and the very first one on the top, it says knowledge advisor. Okay, so let's go ahead and do that. So I go under start, go down knowledgeware, knowledge advisor, and we're ready to go. This is where we write our program. Now notice that in the very top, in this toolbar called reactive features, there is an icon here, which if you look at it, it says it actually says rule, but if you look at the shape of the icon, it says if x y. Okay, so basically it's telling you a program. You can write a program. You click on it, and you can give it any name you want. I'll give it rule 1. That's okay, no problem. And here is the date that's created, which is 15th of July, and etc. You can change it so that it says by whom it's created. That's created by me, and we say okay. All right. Now we start writing our code. So I put the cursor there. I put the cursor on the very right hand side, and I click enter. So this you can write your code line by line in here. Now, what I want to say is that if time is less than, let me go back here. If time is less than 3, this position is going to be the 0 position. Don't move at all. So let's go ahead here. Let's go to our CATIA. Say if, and if you wonder, should I write a capital I, lowercase I? If you click on the keyboard, you see that all the stuff is here. You can also double click on it. It's going to put it up there. But anyway, if. Now, I don't want everything here because I'm dealing with the kinematic. You just click on the mechanism here so that it filters these out. You click on the mechanism on the toolbar, on the tree. Notice that the only thing that's important here is the time and the command. So you want to type this thing over here, but you don't actually type it. You select it, you double click on it, left click, double left click on it, and notice that it puts it up there. So if time is less than 3, don't forget to say S, 3 seconds, okay, 3 seconds, because the dimension of the kinematic time is second. So if you put a 3 on the right hand side, it doesn't know what the dimension is. It's going to give you a syntax error. So if the time mechanism / kin time is less than 3, then we know that the position is 0. Okay, so you hit enter, and then it's double click on this, select the command right there, left double click. So this is equal to 0. Don't forget to put 0 inches. Okay, hit enter. Now you want to say else. Now remember, keywords are here. If you don't remember else, you just select the keyword, else if, right there, else if. Once again, select the parameter, and you type time. If time is less than, look at this diagram, less than 7, right there, less than 7. And don't forget 7 seconds, 7 seconds. then the position is going to be equal to the velocity, right? The velocity, if you look at this figure, it goes 5 inches in 4 seconds. 5 inches in 4 seconds, slope of this line. So what you go in here, let's try it again. Let's try it again. If the time is less than 7, this is the formula that we're using. For example, if the time is 3, we should be getting 0. 0 position, right there, no height, 0 position. If the time is 7, go back here, see what happens. If the time is 7, you go back to this. If you plug in 7 here, you're going to get 0 plus 5 over 4 times 7 minus 3 is 4. So 4 and the 4 in the denominator cancel, and you get 5. Okay? So, else, keywords, else, what do we know? It's going to start at 5 and it's going to go down by a different slope. And the slope of it is 5 inches over 3 seconds, but it's negative. Okay, so you go back here, else, hit enter, and then mechanism, select the parameter. Well, select this mechanism so that everything pops up, all, right there. Select the mechanism, all, double left click on this, equal to 5 inches plus parentheses, or let's make it negative because we know that it's a negative slope, parentheses 5 inches divided by 3 seconds, that's the slope of that line, which is the velocity, times parentheses kinematic time minus 7 seconds, close. Yeah, that's it. Now, if you made a mistake here, a syntax error, for example, if I took this 3 out, right there, you can see that right there. Instead of saying kinematic time less than 3 seconds, 3s, I said 3. It's gonna, and say try to say okay, it's gonna come back with a message saying that there's something wrong here. So you have to go figure it out, and then there should be 3s. Now, assuming that there are no other mistake, yeah, good. So notice what happened here. A rule has been set up for me. I double click on it, and it's the program that I wrote. And we say, okay, all right, good, let's go ahead. Now, before I go ahead, let me bring this up, go there in the animation mode, or in the full scale mode. This is the thing that I want to write the program with, right? Program 4. Here's the program. I wrote it. I made some boo-boos here trying to sort this out, but anyway, there it is. Now, it is fussy. You cannot write, for example, in underscore s to represent inch divided by s. Remember, this is the kind of thing that we could do before. No, you have to write it as 1 inch divided by 1s, or 5 inches divided by 4 seconds. Okay, so it's fussy because 1, keep in mind that 1 does not mean 1 inch. That's why when I remove for example, when I just type right, if time is less than 1, it doesn't understand. So make sure you don't make mistake. You cannot take this S out. You cannot take this 3 out. Okay. So anyway, it is fussy, and that's why you make sure position. If you say length equal to 0, you better put in in front of it, okay? And also don't forget to look at the shift. It's very easy to make these mistakes, but you have to figure it out. Once you plot it, you see that you missed something, and you move on. Okay, let's go ahead, and this is the second problem, which I'm not going to do yet. Let's go back here. Pretty much it. So let's go ahead and actually make a sensor here. Okay, so we're going to make a sensor, the ball going down a ramp. The reference product is that base. The point is this top point. Okay, and then we go to simulation with laws. Click on the activate sensor, and let's say X position, X vertex. Move this thing out of the way. We want to do it over a 10-second interval, 10-second period. So if I want to change it over here, but this is already 10, and play it. There, notice what happened. It went first. Let me rewind this. Let me rewind and show it to you again. Okay, make sure you clear the history. Clear the history. I rewound it, and let me let me play it. The first 3 seconds it sits there, then it goes down here to 5 inches, and then it goes back. Okay, that's the way the rule was supposed to work, and it is. 3 seconds stays there, immediately goes back, and there we are. So if I say, give me the graph, I better get this same graph that I was supposed to plot. So if you make mistakes here and it doesn't complain, that you better look at the results, see whether it's actually doing what you wanted. Otherwise, you have to go fix it. Okay. So that takes care of the first problem, and the first problem was this. As I said, it took us some work to get this thing sorted out, but that's okay. The next thing I want to do is this problem, and we have a rotating arm. We did this problem, except that there, as the second problem in week 2, not week 2, week 7, I believe. We had a constant speed of this arm, but now we don't. So it's constant speed, sits there for a while, and then it goes again at the same speed, by the way. Okay, so let me go ahead and make this thing for you. Once again, I have made these parts, so let me get rid of these, close it. All right, so let me start with the product file. All right, insert existing component, because I already made them in there. And I think the folder that I need is arm rotating right there. And I want the arm and I want the bearing, these two. There we are. Okay, let's go to assembly design. This is a revolute joint. First anchor the base. So we're going to anchor this base. And then we create a coincidence between the axis of this base and the axis of this arm, and coincidence between top of this base and the bottom of the arm. And this is going to turn into a revolute joint. You will see. Okay, good. So now we're going to go to the digital mockup, DMU kinematics, get the magic wand out, new mechanism. Okay, auto create. You say, should I do that? Yeah. And if you check our joint, there's going to be a revolute joint, degree of freedom 1, right there. So the first thing that you need to do is you have to bring this thing to 0. You double click on revolute, make this thing angle driven. All right, good. Then we want to create this this physics, and the physics is that curve basically. Okay, so how do we do that? We go to start, knowledgeware, knowledge advisor. You click on that guy, says rule right there. Give it the name, whatever you want. You can call it arm, for example. Whatever you want. Here, arm rule. Sounds scary. Arm rule, and we say okay. Good. So we know that when time is less than 3, it's a constant speed, 180 degrees over 3 seconds. Okay, so we go here. We say if, I'm sure you don't need to know the keyword to do that. But I bet if you type big IF, it's going to be a syntax error. If and then click on the mechanism here so that we get the stuff on the mechanism. Double click on that. So if time, oh no, time. This is wrong. This is wrong. Backspace, backspace. If the time, that was the command. That's the angle. Select this. Double click. If time is less than, no, I can't remember. Was it 4 seconds? 3 seconds. Yeah, 3 seconds. 3s. Enter. And it's going to be the angle equal to parentheses 180 DEG divided by 3s times time. Enter. Else if, like if it's too much to remember, keyword else if, go back to parameter, else if time is less than, let's go back here, that shift is going to be 7 seconds, less than, put a 7 second, or, so, yeah. So if time is less than 7s, enter. Here's the command angle equal to, that should stay, it should stay put. It should stay at 180 degrees. So it's equal to 180 DEG. Enter. Finally, you say else. Okay. Else. Enter. So it's going to be the angle equal to 180 DEG plus the speed, which is going to be another 180 degrees, 180 degrees in 3 seconds, another one. So it's going to be 180 DEG divided by 3s. Please note that you could have written it as 60 degrees divided by 1s. It's okay, but I'm just trying to look at this graph and exactly say what it is. 180 degrees in 3 seconds. Okay. Times, don't forget the shift here, times parentheses time minus 7 seconds. Let's check it out. For example, if the time is 7 seconds and you look at this expression, the second term is 0 because it's time minus 7 seconds. Time is 7 seconds and the angle is equal to 180 and it's supposed to be right there. When time is 7 seconds, that formula should give me 180 and it does. But when the time is 10, when you put a 10 here, 10 minus 7 is 3. It kills the 3 at the bottom, at the denominator of this. It says 180 plus 180, which is 360. Okay. So let me go ahead here before I say okay and move on. So this is the problem that we're doing. And I'm going to put this thing in the full mode. And just to remind you what happened. That is what we are trying to write a code for. These are exactly the stuff that I typed. Fussy. So be careful about how you write that speed, okay? And remember that units must be specified. For example, 3 seconds, 180 degrees, etc. And don't forget any shifts. Okay, here I needed only one shift. Okay, so that's exactly the same kind of thing that we have. Good. So let's go ahead and run it. And we say okay. If there are any syntax errors here, it's going to pop up when you try to say okay. And sometimes there may not be syntax errors, it's just that plain you wrote the equation wrong. When you plot the stuff, you're not going to get exactly what was given to you. Okay. So let's go ahead and do a simulation. What is that? Do a A sensor, let's do a sensor. So obviously you have to go to the digital markup to do the sensor and stuff like that. You're not in digital markup. So notice that a law has been created. If you want to get to it, left click, double click, you're going to get to it. But I don't need it. So you go to digital markup. Oops, sorry. Let me just. Oh, we're in there now. Good. So sensor, the ball rolling down a ramp. Now this is the reference product is here, and the point is there. We say OK. All right, there is your speed acceleration sensor. Now we go to simulation with laws. Activate sensor. What is it that I want? I want the angular position, right? One way of doing that is to say, actually, you can go down here and find out where the one way of doing that is select the mechanism joint this, select this, okay? I have a feeling that I think if you do, yeah, the only thing that you see angle here is actually that guy, okay? None of these will have angle on it. So it's this one. Because you're plotting angle, just select the first one, just this one. Okay, move this thing out of the way, play it over 10 seconds. Remember, it stops there and then moves again, and then graph it. I better get that plot that I inputted, and I do. Okay, so it goes to 360. This doesn't go all the way to 400. 360 stops here. That plot is identical to this plot, which is good news. Okay, so now we want to put this rotating arm on top of that block and then write some new formulas. Okay, these are not the same rules, but now I'm going to do this thing two different ways. One of them is specify both commands in the same rule. Okay? In other words, single rule, both the command for the position and the angular position specified in it. And then I'm going to come back and repeat it where I have two rules. You might say, well, why should I make my life more complicated? We'll get that to that later on. So let me go here. If I can. Something happened to my mouth here. I think my mouth is acting weird here. Let me take the USB out. Second. Wow. Oh. Let me close this. I'll save it and get back to it. Let me get rid of this. Oh my God. I thought I had to redo this thing again. So close it, close it, close it. Don't save. Let's go back here, open this guy. Lecture 10. There we are. Oh, that's a lot better. Okay. Okay, so I have already made the parts for you. So we go there. So product, we start with the product. Say okay. And insert existing components in there. Now I have a folder called arm and block together, one rule. So basically I want these guys. So all four of them, arm, base, bearing, and the block. There we are. It's the same thing that we had before, except that. Now, let's go ahead and create our assembly constraints. So let me, first thing I'm going to do is I'm going to anchor this guy, space. Okay. Now, notice that this bearing is going to go on top of that. Okay. But I really basically it's a rigid joint between this and that. So here's what I'm going to do. First of all, let me move it up for a second. So for example, this guy and that guy, update. Oh, on the other way around. Okay, no. On the let me do difference. Let me do. Okay, let's try it. Try it again. Well, first of all, we anchored something, right? Let me delete this. Okay. I'm going to do the following. I'm going to move this thing up. Good. Okay. And I'm going to do coincidence between this and that. Update. Good. Now let's make our prismatic joint between these two. Okay. You know what? Actually, move while we're at it. Let me do the revolute between this axis and that axis, and coincidence between the bottom of that and the top of the bearing. This eventually is going to become a revolute joint. Good. Now we're going to do a prismatic between these two, prismatic. So face and face, coincidence between face and face, and coincidence between this edge and that edge. That's going to become prismatic. Good. Now, remember I said that this is rigidly attached to that? One way is to use this paper clip. Paper clip means fixed together. That bearing and this block are fixed together. This eventually becomes a rigid joint when you use the magic wand. Okay, let's go ahead and figure it out. We go to digital markup, DMU kinematic, get the magic wand out, new mechanism, auto create. We say, okay, why did I get 3? Because there is a revolute one up there, there is a prismatic one down here, and there is a rigid one that was automatically created because I fixed them together. Even if I had not done that, I could have physically, rigidly done it myself. Yeah, I could have done it myself. Okay, good. Degree of freedom is 2, no problem. So revolute is going to be angle driven. Prismatic is going to be length driven. And now the degree of freedom is going to be 0. And we have to put the physics into it. By the way, let me show you something. Something that may kind of surprises you. Now look, obviously I can do the manual dragging. This is a 2 degree of freedom system. So this thing turns and this thing moves, right? This thing moves, yeah? Reset. And I can make it make it fool us so that we actually put some physics into it. Let me go and create a simulation. This is not what we want because this is just a plain cartoon. If you drag this, for example, if you drag this, let me just put some number here. Yeah, if you drag this and you drag this thing by 10, roughly 10, the other way. Okay, yeah, good. No. Okay, insert, rewind, play it. It looks like they're working together, and they are, but this is just a cartoon. Okay, so just be careful. That's why we are not asking people to submit animation file, because the animation file, we don't know whether that's a proof of what they have done correctly or not. Okay. All right. You want to see the entire product and all the parts and stuff like that, and see whether it's working. Just a video clip that you may have prepared doesn't mean that actually you did the problem. Okay, so let's go ahead and do that as a single. Remember, we want to put these 2 laws into, or rules into our program. So let's go ahead to CATIA. Remember, we go to start. Where is that? Knowledgeware, right here. Knowledge advisor. click on this if, etc. So this is the rule. I'll call it uh, both in one rule. How about that? Both in one rule, because later on we're going to come back and make two separate rules. Okay, there we are. So now you see that. Remember that? So let's look at, for example, the first 3 seconds. And the reason this is more efficient than putting it in two different rules is exactly because the breakpoints are the same. When I say if t is less than 4 seconds, then I can write the formula for this and the formula for that. If these breakpoints were different, there is a lot of if and then and things like that, unless you break it up into two rules. Okay, so let's go ahead. Let me go here. The first 4 seconds, the velocity is 2 inches per 1 second, or actually where I got this from is 8 inches over 4 seconds. Okay, so let's go here. Let me go ahead. Bear with me for a second. I have to look at my, instead of going back and forth between these, I'm going to look at my worksheet here. So let's go there. We say if time, now you want to get the time information, click on the mechanism, it filters it out. Here's your time, and these are the two commands, right? If the time is less than 4s, enter. Here is your length. The length is equal to, remember I said 8 seconds, 8 inches over 4 seconds, so which is 2 inches per second. So I write it exactly like it is, 8in divided by 4s times time. Left side is inches, right side is inches. Enter. Now I want the angle. Angle equal to, and if you look at this over a 4 second interval, this has gone 720 degrees. So 720 divided by 4, that's why it says 180 degrees per second. So let's go back here. Parentheses, 720 DEG, remember it's fussy, divided by 4s, close it, times time. Enter. I'm going to line these up later on. Okay. Else, here's else. If you don't remember how to spell it, right there. Else, if, let's look at it. If time is less than 6, it's just stay there, stay put. Okay. So if time, select the parameter. If time is less than 6 seconds, don't forget the second, S, the length is going to be 8 inches. Sit there, enter, and the angle is going to be, what was it? The angle is going to be 720, right? 720, right? Okay, yep. So we go 720, 8 inches, and the angle, enter, here's the angle, equal to 720 DEG. Enter. Else, in other words, if now you're past the 6 second interval, both of them will start moving. Else, enter. The position is equal to, now the 8 inches is going to get reduced. 8 inches minus, let's look at our speed. Our speed was, it's going to go 2 inches per second, same speed except that it's negative, okay? Except that it's negative. So it's going to be minus 8 inches over 4 seconds. 8 in divided by 4s. Please note that I can write it as 2in divided by 1s. It doesn't matter. Times parentheses, okay, and the time, don't forget to shift, minus 6s. If you make a mistake, it's going to pop up later on when you plot these graphs, okay. Hopefully that's what I've got. And the angle, here's the angle command right there, equal to 720 DEG minus, now I think the angles, the speed is a little bit different now. This is 360 over, yeah, 360 over 4 seconds. Yeah, it goes to 360 over 4 seconds. Okay, so we go here. 360 degrees DEG divided by 4s. Just keep in mind that you can write this thing as 90 DEG divided by 1s times exact the same kind of a thing, time, don't forget the shift, minus 6s. Close it. Now, when I try to say OK, it's going to come back with a message. You'll see why, and I'll talk about it in a second. This is saying that you have two lines. See this? This is saying that you have two lines, although it may not be giving you that message. It's saying that, look, you have this thing and that thing. I cannot do it. So I have to put these things in braces. So notice that I'm moving my cursor to the on the top. Put a braces, and maybe parentheses will work too. And then we close it on this second line. And I have to repeat this for every time I have two things to do. Braces, and then braces, and then braces, and braces. Hopefully there are no other errors. We say OK, and there we are. You want to see your rule? Double click on it. I want to make this thing nice and organized, so I'm going to tab this thing and tab this thing so that you can see it better, you can read it better, and tab this thing, okay? And we say OK. And the code that I wrote for you is right here. Don't forget these braces. We need it. Okay? So let's go ahead. Let's go back there. Let's go back there. Activate sensor. Actually, let's go and create sensors. The reference product is down here. And the point is, okay, so just 1 second now. We need two sensors here, okay? One for the block, right there. You see that? One for the block. That's one. And I'm going to call this thing, I'll call it block. Say OK. And another one for the arm, the tip of the arm. So another sensor, I'll call it arm. And the reference product is, again, this bottom thingy. And the point is that point at the tip of the arm. Now notice that I have two sensors here. Now, when I go and when I go simulation with laws, activate sensor, if I selected the first two, that's good enough. It will actually produce for me the position and the angular position, okay? These two are actually the commands associated with the mechanism, the rotating arm and the block, okay? Yes, you can go and plot other stuff, velocity and speed and things like that, but I don't want to do that. So I just go and say play. Whoa, oh. You went the wrong direction. We'll fix it. Now, of course, the plot is going to be the same. Okay, this, if you look at this, is exactly, where is that? Exactly these two plots. Okay, And by the way, the next slide tells you that all you need is to activate the first two. Now, let me go and fix this because people may be fussy and say, it's not what I'm doing, etc. Fine, no problem. Let's go back here. Let's go to our prismatic joint. Prismatic joint. There is an arrow here. You flip it. Okay, good. You flip it so it goes this way. And we go back to the simulation with laws. Activate sensor. These are already, the first two are already active. Oops. Move it out of the way. Play it. Yep, yep. Okay. And then graph it. And these are exactly the same plots. There, exactly the same plots. So I want to go and repeat this problem, but I'm going to write two separate codes. One rule for the block and one rule for the arm. You might say, wait a minute, why do I have to do that? Notice that if my rule, let me get rid of these. Rewind, close it. If my rule was at different breakpoints, 4 and 6, 4 and 6, instead of 4 and 6, this was 5 and 8, then I needed a lot of if statements. So it's easier if I actually go and create two separate rules. So I'm going to do that for you. All right, let's go back to this. And I'm going to minimize, well, let me just delete the mechanism. How about that? I mean, let me delete this mechanism. It's easier if you do it like this. Don't delete the children. Don't delete the children. Okay, good. All right. So now we go to the digital markup. DMU kinematic, magic wand, new mechanism, say OK, auto create, say OK. So let's see what we got. We got the same joints as before. That doesn't surprise us. Revolute joint, we want to make it angle driven. Prismatic joint, we want to length driven, except that let me flip this arrow so it goes in the other direction. Okay, good, good. Now obviously degree of freedom is 0. No problem. So what do? We go to start, knowledge where, knowledge advisor. Here's the thingy. So what I can do is, I'm going to do that in a second, but if I go to the program that I wrote, those rules that I wrote, and just deleted the second command, which was for angle, that's all I need for the block. And if I deleted the first line, that's all I need for the what is it called, for the arm. Now the problem is that there is no cut and paste, copy and paste. There is no copy and paste. So unfortunately, I have to type these again. Okay, so if you go down here, this is how it's going to look like. From the block, I remove the second line of each of these ifs, and for their arm, I deleted the first line of each of these. So unfortunately, I have no choice but to do it. All right, so let's go ahead here. Click on this, and I'm going to call this thing block rule. How about that? So that I know what I'm doing. Block rule. Say OK. All right, let's do the stuff for the block. If time, click on the mechanism so that you get all the filtered out. If time is less than, now I have to look back and forth. I think it was is less than 4 seconds. Yeah, less than 4 seconds. 4 seconds. Yep. The position is equal to, what was the speed? It was 8 inches over 4 seconds, right? 8 IN divided, literally divided by 4s times time. there. Else, if, again, time is less than, now that was 6 seconds, 6s, enter, length is equal to, sit there, 8 inches, enter, else, length is equal to 8 inches minus, because it goes backwards, parentheses, and the speed is the same, 8 inches over, it was the same, 8 inches linear speed, 8 inches divided by 4s, times, parentheses, time, don't forget to shift, minus 6, I'm sure 6s, yeah, minus 6s, yep, 6s. Yeah, that's good. And hopefully we notice that I don't need the braces here because it's a single line, single line, single line. In the previous case, I had 2 lines to be considered, and I had to put them in braces. This one is okay, assuming that I don't have any other syntax error. Yeah, that's good. There's the first one. Click on this thing again. Call this thing the arm. Arm. Say okay. And I do exactly the same thing except that it goes for the angles. So if, unfortunately, there is no copy and paste, so I have no choice but to do it like this. So click on the mechanism. There's the time. If the time is less than 4 seconds, enter. Here's the angle. Angle equal to, it was 180 degrees per second, or 720 over 4. Remember that? It was 720 DEG divided by 4 seconds, or 180 divided by 1 second, times time. Oops. Okay. Enter. Else, if time is less than, now it's 6 seconds, enter, angle equal to, it starts at 720 degrees, remember, right there. Where was it here? Starts at 720 and it goes down, okay? That's why I have it like that, 720 degrees minus a negative speed, right? Negative velocity. So it's going to be 360 degrees in 4 seconds. Divided by 4 seconds, parentheses, times parentheses. Remember, don't forget these math operations. Minus 6 seconds. And hopefully I did not forget anything. Yep. Oh, wait a minute. Wait, this, if the time less than 6, this actually sits there. That's not right. Okay. Enter. Else. Yeah. Now, this is not SL. Else. Get a syntax error otherwise. Angle equal to 720. Now I need the DEG minus, that's the thing that I was going to, I typed a minute ago, I have to erase it. 360 DEG divided by 4S times times parentheses. There's the kinematic time minus 6s and close it. Hopefully I don't have a syntax error. We'll find out. We say, okay, yep, right there. You can see that. Now we're going to go and to digital markup, DMU kinematic. Actually, I'm there. If I double click on this thing, I should be ending up there. Yeah, right there. Okay, good. I'm there. and I have my rules here. You can see that. By the way, these also appear up there. This is the old one that I did. Actually, I can delete this. I can delete that. These are the new ones that I did. Okay, good. And sensor. So the sensor, or I deleted everything. Sensor. So it's going to be one of them is going to be uh, uh, you know what? Let's check something. Let's make one of them and see whether both will appear there in that list or not. We'll find out. So the reference is this, and for the block, I selected that point, and I'll call this thing block. Block. We say OK. All right. I may need the other one, but I want to check something to see whether we can get it with one, which I doubt it. I doubt it. We'll find out. So let's go to simulation with commands. Activate sensor. Yeah, okay, we have both of them right there. So I really didn't have to do two because both of these commands are here. These are the things that I want. Yes and yes. Okay. And play it. This is with two rules. You can see that. And graph it. Yeah. Okay. So if you need information, yeah. Actually, let me close this thing and scroll down here. See, this does not give you anything about the arm, but if all you want is the position of the arm, it's already there. But if you wanted to know the velocity of the tip as a function of tip of the arm, as a function of x, or as a function of time, etc., you have to create a sensor for it. But these are the joint commands that it appears here. So did I plot it? Yeah, right there. That is exactly what we got before, and it's a confirmation that we did whatever we did is right, and exactly the same as it ought. Duh, right? Now, I ran out of time, so I'm going to stop here. I had two more things that I wanted to do, one more thing that I wanted to do, but I didn't put it in the agenda because I didn't think we are going to have time, and I don't, and I'll talk about it later on. Because this business of putting intelligence into the CATIA program is beyond just this mechanism. Even for part design, you can do that, okay? For making parts of saying if this happens, radius of the fillet equal to that. If the length of the box is this, the pad height is this. So basically, you have to write some C codes. We'll do that later. All right, folks. So good luck.